Okay. Hello, everyone. Good morning, good afternoon, good evening. This is day 3 of the Global Hands-on Universe Conference. We have another 2 sessions today, and we start with a keynote talk, and I will ask my colleague, Rosa Doran, to introduce our speaker. So good morning, Rosa.
Good morning, Gustavo. Good morning, everyone. Here we go again, another exciting day ahead of us. Starting with an exciting keynote. Really looking forward to this day. So, good morning, everyone, wherever you are. Good afternoon, good night. Hope you all have your coffees, your teas in your hands, and you're ready for the day. So we start with a very nice presentation, students as planetary defenders. This is always exciting to transform students in planetary defenders. And we have with us to present that, Daniele Gardiol. He's an astronomer at the Italian National Institute of Astrophysics. He has a physics degree, and he has spent a lot of time designing and building astronomical instrumentation. He was part of the commission group of the Italian National Telescope Galileo that is located in the Canary Islands. If you haven't been there, join us for the Canary Islands training. It's a beautiful site. And he was responsible for the instrument model of the astrometric ESA mission Gaia. He's currently the national coordinator of PRISMA, which is the Italian fireball network that is dedicated to the observation of bright meteors and the recovery of freshly fallen meteorites. So far, the project recovered 2 meteorites, which is awesome. And these are part of a group than less than 50 meteorites recovered in such methods worldwide. He's also heavily involved in outreach and educational activities on the subject of minor bodies in the solar system. And this is what he's presenting today. Another project where, we have kids becoming discoverers of meteorites, hopefully. So Daniele, is this the case to say that you really rock? So welcome to Global Hands-on Universe, and I give you the floor. I'll let you know a few minutes before the time ends, so we still have some time for questions. Thank you for joining us.
Okay, thank you so much, Gustavo. Thank you so much, Rosa. Can you hear me?
Perfectly.
Oh, wonderful. Thank you so much for inviting me. Welcome everyone to this morning session. Yes, I'm presenting this exciting project that we are now very pleased to give you this information about the project and the content of the project. So I'm giving the talk, but this is a joint effort of the Italian team of the STAND project. Also, my colleagues Dario Barghini and Carla Berti contributed to the presentation. So I will briefly describe the STAND project and the PRISMA network that was mentioned by Rosa, and what we specifically developed as enough for the project, and give a brief overview of the asteroids and meteorites scientific, let's say, aspects. And then at the end, I will provide you with some ideas for the scenario that can be used by teachers in the classrooms related to this activity. So first of all, STAND is an Erasmus Plus project. I don't know if each of you know the Erasmus Plus program. It's a program of the European Union that is financing projects in the area of education, training, youth, and sports. So it's a project funded by the European Union. We are 5 partners besides ENAF. We have the COSPAR, which is the Committee on Space Research, which is a worldwide association, but it's based in France. So technically it's a part of Europe. Then we have a German partner, which is FTP Europlanet. We have a school in Greece, the Lino Germaniki Agogi, and of course Nucleo, which is also one of the organizers of this conference. What are the objectives of the project? So, of course, the first strong point is to try to engage the primary and secondary school students and also teachers in the subject of asteroids, meteors, and in general of planetary defense. Planetary defense is, we call it all the efforts, so the activities and the action that are made to monitor and protect the Earth from external space threats, such as asteroids, comets, and also other objects in space. This is done in order to raise the interest in science and space exploration. I don't know the situation in other countries, but for example, in Italy, we have a few students that decide to enroll in university, for example, in STEM subjects. So this is particularly important in Italy to try to improve the number of students that want to become scientists, let's say, strictly in brief. And so the idea is also to improve the competencies of the students in these subjects in order to encourage them to join a university course in science. So we have two main targets. Of course, the targets are the schools, both the teachers. We are forming the teachers in order to enable them to bring this activity to the students, and of course, directly the students. The main targets are the 5 European countries that are the part of the partnership. The activities of the project, well, we will provide the teachers with a toolkit. So we are, it's almost done. We have a toolkit that will be distributed to the teachers in order to support their activity with the students. At the same time, we will have the so-called STAIN Academy, so which is basically the training activities for the teachers, and implementation, which is the real implementation that the teachers will do in the classrooms, in their classrooms. So regarding the formation of the teachers, we have an intensive formation. We have 3 main aspects. One is a teacher manual that is already ready, and that will provide to the teachers, let's say, a theoretical basis on the subject of asteroids, meteor, and meteorites. It's also foreseen to have books, massive online open courses, so that the teacher can either online but also offline get answers, interact with us, and in order to get answers to their questions, doubts that may have. And also immersive and intensive summer schools. We already had one. You see a photograph here of the recently done school we had in Greece at the beginning, at the first week of July. That was a very nice school, and we had the possibility to test our formation tools. The toolkit, as I mentioned, the toolkit are a collection of practical activities that we are proposing in the schools. We have 3 main part of the toolkit. One is the so-called micrometeorite kit. Is a kit for collection and study of micrometeorites. Those are very small spheres of space material that can be collected basically in the mud. So we will provide with a kit that you can use, as you may see, your cell phone to make this study. You can connect it to a microscope and try to find out the micrometeorites. We have the camera kit. This is on the right part of the screen. These are cameras, all sky cameras that I will speak more about these later, because this is responsibility of INAF, that are can be installed and will be installed in schools, and are able to detect meteor and compute the trajectory of bright meteors. We also are proposing asteroid search campaigns that are performed using remotely operated telescopes. There are two types of activity. One is the discovery of new asteroids by making observations, and the other one is the follow-up of already discovered objects. The follow-up, even if can be less exciting from the point of view of it's not really a scientific discovery, no, but it's very important because enables the astronomer to compute the refined orbits of already known asteroids. The orbits can be predicted only in a few time span, so it's very important to continuously follow the movement of the objects in order to be able to predict their position in the future. And we will also prepare scenarios for the teachers. They are preparing their own scenarios, but we also propose example scenarios that can be used with the students. So this is one slide only to briefly tell you what is INAF. The National Institute for Astrophysics is a public research institution, and in INAF we basically do, it's a national, so you can see here all the cities where we are present in Italy. This is a quite recent institute. It was built in 1999, so it has 25 years, 25 years old. And of course, we make astronomy is much older in Italy, but are now are part of INAF, all the historical observatories in Italy. For example, Padova, Bologna, Firenze, which are the oldest one, but also more recent. We do basically three things. One, of course, is research in the field of astronomy and astrophysics. We do technology, so we build new telescopes, new devices to study the universe. Of course, since Galileo pointed a telescope to the sky at the beginning of the 17th century, astronomers are developing and designing, building their telescopes and the devices to go to look for weaker objects, to look farther into the universe, to make new discoveries. And of course, also, as you can see, outreach and education. This is why we are involved in this project. And I come to the subject of let's say, our responsibility in the STEM project, which is the meteor camera. You can see here in this image the meteor camera kit. So you have the camera itself. Number two, it's an all sky. So this camera is able to make one picture of the full sky in one single picture. Of course, the picture is distorted, but it can be calibrated, and it is important because we don't know where the meteor are located in the sky, and so we need an image of the whole sky to be able to find them and spot them. The camera is controlled by a local computer. This is let's say, a normal personal computer, just smaller, because the camera operates at 30 frames per second. So it would not be possible to remotely control the camera. So when a meteor is identified, the images are saved onto the hard disk of the computer, and then all the nodes, all the cameras are connected to a central server, and the images that are temporarily stored on the control computer are sent to the central server through the switch that connects the system to the internet. In fact, we have this Prisma fireball network in Italy, which is based on this kind of cameras. We have roughly 70 stations equipped with these cameras, and we are continuously monitoring the night sky in Italy. This project started in 2017 and is led by INAF, but it is a participatory project. We have more than 65, 70 institutions collaborating to the project. So we have professionals like researchers in other research institutes or universities, but also a lot of amateur astronomers, schools. That's why we are proposing to install this kind of camera in schools, also for the STEM project, and even private citizens. So the stand camera will rely on the Prisma know-how and Prisma infrastructure. So this is what you can see in the sky, what it is in the sky, even if you cannot see them in our solar system. Those are bodies and the effects of what these bodies can produce, and they are called the minor bodies of the solar system. In our solar system, we have the sun, we have the major planets, we have the so-called dwarf planets, and we have a large amount of smaller bodies. So we have, as you of course already know, we have asteroids, we have comets, we have meteorites, which is the name that astronomers used for a small asteroid. So meteoroid means a small asteroid. We have micrometeoroid, which is very small. We don't call them asteroids because they are too small, but it's just a matter of names we are giving in order to our categories. No, we human need to describe the reality and also the universe by using categories. What happens when one of these bodies, hopefully a small one, enters the Earth atmosphere? We have a falling star, or what we call technically a meteor. So the meteor is the light, physical phenomenon of one of those bodies, a small one, entering the Earth atmosphere. When the body is not so small, so for larger bodies, this meteor becomes very, very bright. And so we call them fireball. So it's a meteor conventionally brighter than the planet Venus, which is a very bright object in the sky. It's the third brightest object in the sky after the sun and the moon. And if it is really, really bright, then we call it a bolide. So in general, these objects burn completely in a fraction of a second or in a few seconds due to the friction of the atmosphere. But if they are large enough, so let's say bigger than a football ball, more or less, 20, 30 centimeters. So it's quite a small object from astronomical point of view, but already a large object. They can, they burn, of course, but ablate, but at least a part of the original body can survive and fall onto ground. And this is what we call a meteorite. So a meteorite is the remnant of a meteoroid, of an asteroid that after their burning into the atmosphere. So let's start from the comets. For sure, you know that what comets are. There is a comet that is foreseen to be seen very bright in the near future. They always say, there will be a very bright comet, and then we are always deceived. But one day, a very nice comet will come again. I remember the comet in the 97. The Hale-Bopp was a real spectacle in the sky. So these are objects that are formed in colder regions, very far from the sun, 1,000 astronomical unit, more or less. It means 1,000 times the distance of the sun and the Earth. There is a cloud that was so-called Oort cloud, from the name of the astronomer Oort, we have never seen this cloud, but it's an hypothesis where these cometary nuclei are there and are like a reservoir. And now and then, due to gravitational perturbation, some of these cometary nuclei fall onto the sun and can show a cometary activity. No, and this is what you can see as an effect of the cometary activity. The comet, when the comet is near the sun, it's heated and bombarded by the solar wind. Those are small particles, protons mainly, that bombard the comet nucleus. And so the comet is fragments and loses small fragments. And when those fragments collide with the Earth orbit and enter the Earth atmosphere, we have the meteor shower. So a lot of falling star, shooting stars that we can see. Here you can see, for example, if you leave a camera open, taking a long time exposure picture, you can see all the shooting stars during one night. Those are the Perseids, renowned and famous shooting stars of the middle of August. And you can see that they all seem to come from one point at the center of the image. This is the radiant, so-called the radiant. So the path of the shooting star is not random, but is very, very well defined. And this is because the Earth is moving towards a given point. And those are seen as if we were on a road, moving at a high velocity. We can see the trees, what's in the around us, running very fast around us. And this is exactly and what the first one to discover the connection of the shooting stars with the comets was an Italian astronomer, Giovanni Schiaparelli, and it was quite astonishing that this connection of the shooting stars with the comets has only been discovered quite recently, the second half of the 19th century. But besides comets, we also have asteroids. For sure, you know that we have a lot of small bodies that are mainly confined between the orbit. This is what usually students at school are told. No, the main belt of asteroids is between the orbits of planet Mars and the planet Jupiter. As you can see, there are the gray dots in this image. And this is, well, true, because we know that the vast majority, 90% more or less, of the known asteroids are in this area. But we also have some of them in other positions. And how big are they? So we have, let's say, few big asteroids. Here you have an image. No, you can see here the larger one, which is roughly 1,000 kilometers in size. It's Cerere, the first one discovered. And then as you go to smaller sizes, you have a large number. For example, asteroids of the diameter of 1 kilometer, it's estimated that we have 1 million of them. Of course, the smaller, the larger the number. This is due to what we call a collisional equilibrium, because these asteroids, they are quiet and calm, but now and then they collide and they fragment. And so this fragmentation provides, at the end, the collisional equilibrium provides the rate of the number of asteroids for a given size. And also there are other important things that were discovered by the astronomers related to the asteroids and the main belt asteroids. You see here in the graph on the left, every point is one asteroid. And you can see on this axis, the distance from the sun, so the semi-major axis, the distance from the sun in astronomical units. So this means 2 times the distance of the Earth from the sun, 3 times, and so on. And on the y-axis, the inclination of the orbit. And you can see that there is a clustering of asteroids. So those are all asteroids from the main belt, but you can spot that there are other clustering of asteroids. Clustering, I mean, there are a lot of asteroids that are grouped in and have similar behavior. So this is the main belt, the larger black area, but we have other regions where we have a clustering of asteroids. This is, for example, called the Hungaria region, or the Hilda region, or the Siberia region. And we have a lot of, and this is, it's not really clear, but one hypothesis is that this was one large asteroid with a given orbital property, so a given orbit. And this asteroid broke for some reason. And so all these small dots are smaller asteroids that are related to the original larger asteroids. And you can see also there are white stripes here. So these are forbidden regions, regions in which asteroids are not allowed to stay due to the gravitational influence of Jupiter. So this is just to say, it's quite technical, but it is just to say that those asteroids on astronomical timescales are not quiet there. They can move from that region and move, for example, on inner orbits. Due to gravitational interaction with Jupiter, for example, they can be launched outside the solar system or inside the solar system. And those who are injected into internal orbits are the so-called near-Earth objects. Near-Earth objects are asteroids, comets, but the vast majority are asteroids that are near the Earth. We have discovered more than 30,000 up to now. And of course, those are in principle dangerous asteroids because they can hit the Earth. And among them, we have, because of course, this is near, but not so near, 1.3 astronomical units. They are close, but not that close. But we have, for example, 150 which are larger than 1 kilometer in size. So they are very large asteroids. We call them potentially hazardous asteroids. These are the real asteroids that in a near future, when I say near, I do not mean tomorrow or in 1 year, but in astronomical time, in few thousands years could hit our Earth. And of course, they are dangerous. And in fact, this is the timeline of the discovery of all these NEOs by the different observing facilities. And you can see the number is increasing. Only in the last couple of years, the number is becoming more stable. Of course, I'm sure you know that 66 million years ago, there was the extinction of so-called KT extinction, the extinction of the dinosaurs. And now we know that it was an asteroid that was 10 kilometers in size that was responsible for this mass extinction. Those two guys here on the right, the Alvarez, son and father, in Italy, they found the evidence of this because of anomalous amounts of iridium in the KT layer. And then afterwards it was found that the crater, the size of the crater, which is in the Yucatan Peninsula, roughly 200 kilometers. So we already know that this has happened and can happen in the future. Hopefully in the very far future, we hope. And so what the astronomers did is to define, in order to be able to define the danger, how dangerous an asteroid is, we define the scale. This is called the Torino scale. And you can see, of course, the colors are it's obvious, no? So white is no risk. One is a very small risk. The yellow is okay. We have to be to pay attention to what's going on, and orange and red are of course the two main parameters are the energy, kinetic energy, and this is directly related to the size, and the probability of impact. So if the probability is very low, there is no danger, but as soon as the probability increases, we start having a higher danger. So here it's I will briefly go into what happens when an asteroid or even a small asteroid, a meteorite, enter the Earth atmosphere. So we have, as I said, we call it a MET. We can have light emission, we can have shock waves, we can have seismic waves. All the phenomenon, the whole phenomenon is called a meteor. We have a first phase, which is the orbital phase. So this is before the object enters the atmosphere. So asteroids and meteoroids have what we call the prograde orbit. So they orbit in the same direction of the Earth. And so when they hit the Earth, they hit it at a low velocity. When I say low velocity, I mean of the order of 11, 10, 20 kilometers per second. Comets usually, not always, but it's more frequent, that have retrograde orbits. It means that they orbit around the sun in the opposite way, and so they have, when they hit the Earth, a high velocity because it's a head-on impact, and we can reach relative velocities up to 72 kilometers per second. Then we have, while entering the higher layers of the atmosphere, from 300 to 100 kilometers roughly of altitude, the atmosphere is very rarefied. So there are a few air molecules, but at those velocities, nevertheless, the body starts to heat. Starts to decelerate a little bit. But then what is the real meteor phase, when we see the light of the shooting stars, is when the object reaches below 100 kilometers. So the body reaches high temperatures, thousands of degrees, evaporation starts, the body starts melting, particles are subject to ionization, and so the body becomes visible because it emits light like a lamp, basically. Pressures are very high, and so the body can undergo fragmentation, flares, and there are two possibilities to end this ablation phase. One possibility is the body ablates completely, so the body is completely gone, and therefore there's no longer a mass to provide to sustain the energy loss, and so the meteors vanishes because the body vanishes. But there is also another possibility, which is quite rare, but it can happen for larger bodies, is that the light ceases because there is still a body, so there is still a mass, but the velocity is below a given threshold, which is roughly 4 kilometers per second. When the body is decelerated down to less than 4 kilometers per second, the energy produced is no longer able to sustain the light emission. So the light emission ceases. In the lower atmosphere, usually they reach heights of roughly 20, 25 kilometers. So in the span of 100 to 20 kilometers, there is the light emission. If the body survives below 20 kilometers, starts what we call the dark flight. So the body still falls towards the ground, but we cannot see any longer because it is not able to to create lights. At the end, the body falls in free falls, so the cosmic velocity is completely gone, and it can fall to velocities depending on the size that can go from 100 to 300 kilometers per second, which is still high velocity, but it's quite less with respect to the cosmic original velocity. In that time, it is sensitive to wind, so it is moved right and left, forward and backwards. And at the end, it's ground and becomes a meteorite. Which is the rate of such small impacts? Here is an image of explosions in atmosphere reported by military satellites from the US. And you can see a large number. There are much more than we can think. This is in the last less than 40 years. A lot of impacts. The color depends on the energy, and you can see here a large impact, a red one, which happened in 2013 in Siberia, in Russia, and this is the so-called Chelyabinsk superbolide. This is quite important, quite famous because, well, it has been recorded by a large number of cameras. Just to give you a few numbers, it was a 15 meters in size asteroids. So astronomically, very small asteroid. Speed was roughly 30 kilometers per second. But the energy carried was 30 times the Hiroshima atomic bomb. They were able to recover the larger fragment of there were a lot of small fragments because the object underwent 3 subsequent explosions, but they were able to recover half-ton main mass of 70 kilometers from the explosion site in the Chebarkul lake. So we learned a lot from this event. These objects are very difficult to be seen because they are very small, they are very dark before they hit the Earth. Up to now, we only have 9 objects that were discovered before the impact. The first one was in 2008, quite famous, the Alma-Ata Sitta. They were able to compute the area of fall, and it was 3 meters roughly from 2.3 to 5, the estimate meter asteroid. And you can see the last one was in September this year. These are discovered by chance because maybe amateur astronomers or they were lucky. They were looking in a portion of the sky where they discovered the asteroid. But in general, it's very difficult to see them before the impact. Okay, and how can we observe these meteors? So the first photo, of course, by naked eye, and we can enjoy the show, but we can take photos. So the first photographs were made in the end of the 19th century. Then, of course, the technology improved in the 50s of the last century. We had the so-called multi-station observation from the Czechoslovakian astronomers. And in 1959, thanks to this observation, they were able to recover the first meteorite. So after that, a lot of fireball nets, so-called fireball nets, so network of cameras for meteor observation were deployed in several countries. And today, roughly 2% of the Earth is covered by fireball. If you think it's very, very poor, but 70% is made of sea, so we cannot use them. But anyway, even with this small amount, we are able to spot meteors and to recover meteorites. But what should we observe those meteors? I already told you, because it's very difficult to discover very small asteroids. So asteroids larger than 1 kilometer, we know them more or less all. We are 95%, we know them. But the small ones that are asteroids that can be dangerous, even if they are, let's say, small, but they can be very dangerous. Well, for example, 100, 300 meters. So it's 10 times, 20 times the Chelyabinsk asteroid. We don't know how many of them we have. We only have a very small sample. And the only way to be able to understand how many they are and where they are is through fireball networks, observing their entering their the meteors they produce when they hit the Earth. The other thing which is very important is that we are able to compute the area where possible meteorites can be found. So we have more than 70,000 meteorites, but only a few of them have been seen. So those are false meteorites that were seen. The vast majority are finds, and so we don't know where these meteorites come from. And the meteorites are very important because through their classification we can understand what is the composition of the asteroids, and astronomer can study the formation and the evolution of the first time of our solar system. So it's like they are bringing us information that is from 4 billion and a half years ago. So they are very important for the study of the early formation of our solar system. And in fact, we can have what we know, for example, is that we have different types of meteorites, and these different types of meteorites reflect the different types of asteroids and the history that these asteroids had. So through the meteorites, we can study the small bodies of the solar system and their evolution with time. Okay, but why don't we simply go to the asteroids and get a sample of the asteroid with the space mission? This can be done, but it's very expensive. So what we do with the fireball networks is that we can recover meteorites at a price which is less than 1,000th time less than what you will spend with a space mission. And also it's important to recover freshly fallen meteorites. So you see the meteor, and after a few days, if you are lucky, you can recover the meteorite. And so the meteorite is not affected by the terrestrial weather, by what happens on Earth. So we can recover a lot of meteorites in the deserts, in Antarctica, but they are very old, and they have undergone a lot of bad things on Earth. So let's go back. This is an example. This is an example of a meteor seen by a camera of our fireball network, and you can see it's a video. No, you can see the stripe here, but it's a video. So we can save all these images like a movie, and this is the basis for the scientific data reduction. As I said, 30 frames per second during nighttime. The detection is automatic. In the meteor video, you cannot see the star. So what we do is to perform also long image exposure for calibration. You can see here a time lapse where you can see the stars. In this way, we can have a reference for the frame, and we can compute basically the trajectory with the reference frame. So this is what we call a camera calibration. We have to identify the stars via a catalog, and there is an automatic program that is able to to compute the exact position in the sky of the meteor. After that, the meteor is analyzed, so we have the video. We can recover the position and also the light, so what we call the apparent magnitude, the light curve. By combining different observations from different camera, we can triangulate, because of course with a single camera you cannot say where the meteor is, because you see the image, the video projected onto the sky. But if you have 2 or more observations, you can combine them. And this is an example of a trajectory, a 3D trajectory. No? And we can be as precise as 100 meters. It seems a very loose precision, but take into account that the distance is typically 100 kilometers from the observer, and the velocities are of the order of tens of kilometers per second. So this is a quite precise measurement of the trajectory. This is how we do it. So the idea about, we can skip this one, it's not really interesting. I can, if you have questions on that, I can recover later on. One important thing is we can, applying physical models, we can interpret the data, basically the velocity. You can see here a graph of the velocity with the height, and of the light with the height. We can apply models and recover the physical quantities. For example, the shape, not the shape, but the mass, the ablation rate, and other physical properties that allows us to understand the characteristic of the object that entered the atmosphere. And also we can compute the pre-atmospheric orbit. So only in this case, for these few objects, we can, we really know where they do come from, which part of the solar system they belong to. Because for the vast majority of the meteorites, we don't really know. We know that they come from the main belt of the asteroids, but we do not have the precise orbit. With this fireball network, instead, we are able to precisely determine the position in the solar system of the object prior entering the atmosphere. So this is an example. For example, it was our first meteorite recovered with the Prisma network. It was the 1st January 2020. Cavezzo Bolide. You can see here an image of the northern Italy, and you see the red line is the trajectory. And this was seen by these 8 Prisma cameras. And we computed the area where we said meteorites could be found, what we usually call the strewn field. And in fact, the meteorite was found here where the violet star in the lower part of the strewn field. This was really a success. It was really nice, but the nicer thing was that it was recovered by a dog, because the dog smelled well, they have sulfur, so they can be smelled by a dog. And these are the two fragments that were found by Mr. Davide Gaddi, which is the owner, and they were found here. So he's now showing you where he was able to find meteor, because we told everyone in the area, have a look tomorrow morning in your garden. If you go for a walk, look for a black small stone. It may be a meteorite, and it was a success. We were able to, and we are still friends with Davide. Now Pimpa is the name of the dog. She is now 16, and she's no longer able to walk, but and we are very sad about that. So what we will do, of course, we will not provide the teachers with all these complicated things, but we will provide them with a data visualization tool that is able to show the data both of the stars and of the meteor, and will also be used by the students in order to spot the meteor on the images and to compute in a simpler way the trajectory and the luminous the light curve. Now the astrometry is something quite difficult from the mathematical point of view. So for example, what we are proposing as a scenario for the students is to introduce the concept of triangulation. So the idea of how the camera works in order to compute the trajectory by an experiment using two theodolites self-made, and introduce the students to basically measuring a distance with the method of triangulation of the parallax, which is the method that astronomers use to measure distances of stars, of whatever in the universe. The second one that is quite interesting, and is also can be done by a school student, is to compute the light curves of the meteor. So you see here with time the evolution of the brightness of the meteor by using aperture photometry. So another thing that astronomers do is to compute the light coming from the stars. So we will teach the students to very basic way that astronomers use to compute the position and the light of objects in the sky. So I think I'm done. This is a composition of pictures from our first summer school held in Greece in Marathon in July. Those are 3 teachers from Italy that participated into the schools. There were other teachers from other countries. And this is an image of the camera with all those people there. So you can see what will going on in our schools in the next year. So thank you so much.
Daniele, thank you so much for this wonderful presentation. I learned a lot of things. I'm always learning when you are presenting things about our travel companions, this little rock that you know, can hit our head when we go to the supermarket. Well, it will be good if it was that easy. I had one experience in 2019, I think, where we were invited to hunt for meteorites in Provence, and it was such a thrill. I was just thinking, I felt like I was a child. I felt like, okay, why don't we do that with all the children? I mean, this is so super fun and so super useful, and a very nice way to make them understand what's the meaning of being humans, where this all come from, you know, all this remain of the formation of our solar system. So you made a very comprehensive presentation, giving us a very nice vision. And I didn't know it was a father and son close to that, well, not a proof, of very strong evidence of what decimated the dinosaur. That is also super cool. So thank you so much for your presentation. I think it was very enlightening. Let me see if we have questions here in the audience. Well, we have, of course, a lot of people clapping for your presentation. Yeah, Gustavo already asked online on Facebook. We still have not everyone awake, I guess, in other signs of the world, so there aren't questions. I have one. I'm sorry if this might seem a little bit dumb, but you mentioned that you find a lot of these rocks in the poles and in the desert, where it's, of course, it's easy to track and find them. But you said they're old. Okay, we know they're old. They're 4.5 billion old rocks. But how do you know? How do you measure for how long they've been on planet Earth? How you identify that? Because I suspect that you find rocks that landed on Earth in various different times, right?
Yes. Yes. Okay. How do you know when the meteorite fall? You mean how old it is? Yes. There is a way. There are several ways. One is because what happens is that the sun, as long as they are orbiting around the sun, they are bombarded by the sun wind. So the particles, those particles, protons basically, hits so-called targets, for example, iron and nickel, that are on the asteroid. producing isotopes. Some of these isotopes are radioactive, so they decay. And some of these isotopes are created only with this process. They cannot be created on Earth. We have, of course, decay chains on Earth, the one of uranium. So these are terrestrial radioactive isotopes, but we have cosmogenic, so-called cosmogenic. So they are created outside the atmosphere. And so there are several of them. One of the is quite, you find it in every meteorite, in every asteroid, which is aluminium-26. May say nothing to you, aluminium-26, but aluminium-26, if you are able to compute the quantity of aluminium that is expected to be on the asteroid, you know the decay, so you can draw a curve, and you can measure the quantity, the abundance of aluminium-26 nowadays in the meteorite. So you know how much aluminium, the abundance of the aluminium-26 you expected when the asteroid was orbiting the sun. You measure nowadays, and you know that every 700,000 years, the amount of aluminium is half, because and so you can go back and say, okay, this meteorite fell 1 million, 2 million, 10 million years ago. This is a way. And this is just an example. You have several isotopes with different half-time decay, so that you can go shorter times, larger times, and it's not really precise, but a good indication of the time of fall of the meteorite. That's using radioisotopes.
Nice. That's super, super nice. But of course, many of these are created or produced when the rock is falling through the atmosphere, right?
No, they are produced. Those I am speaking about, they are produced when they are outside. They are orbiting the sun, and as they are orbiting the sun, they are bombarded by the sun particles, by the wind, sun wind, the solar wind, and this bombardation generates these cosmogenic isotopes.
Okay.
And this is also why, by the way, we can be sure that the meteorite we recovered in Cavezzo, the one I showed you, is really a recent fall, because somebody said, okay, but maybe somebody bought the meteorite and then said, I found it. But we are sure, because we found one isotope, which is vanadium-48, by the way. And this vanadium-48 is a short-lived isotope, because it only lives for 16 days. But we found it, so we are sure that a few days, few weeks before that meteorite was an asteroid rotating around the sun. So we can learn a lot from cosmogenic isotopes.
I love science. This is awesome. And another thing that just for us to understand a little bit better, how do you know precisely where the meteorite came from, the moon, Mars, or comet, or whatever in the solar system it came from?
Okay, so for in fact, for the large majority of the meteorites, we do not know the object, the original object. We only know for the moon, because we sent spaceships to the moon, even astronomers, and they were able to collect moon rocks. So we can, by comparing, we understand that those meteorites are lunar meteorites, comes from the moon. The same applies to Mars, because we sent on Mars. So we can, by comparing, we can, they're very, very, it's very rare to find a lunar or a Martian meteorite.
Oh,
and
I didn't know that.
Yeah, and also from a large asteroid, which is Vesta, asteroid Vesta. It is quite large, so it can be. We can have spectroscopic observations of this asteroid, and through the spectroscopic observation from ground telescopes, we can understand the composition, we can derive the composition, and we can compare with the meteorites. So there are some classes of meteorites, eugenite, I don't remember the names, that we know that very probably they come from Vesta. But for the large majority, we know that they come from the main belt, probably, but we are not, we cannot say which one of the asteroids was.
Okay.
While with the meteorites recovered with fireball network like Prisma, there are less than 50 in the world up to now, we can compute the orbit. So we really know where do they come from.
Awesome. This is super awesome. Well, thank you for the work you do.
Rosa,
You need to
just,
move forward, right?
no. Yes, we need, but I think there's a very important question on the chat that it's related. Daniele, suppose someone finds a freshly found meteorite.
Yes.
What people should do, because that's related to the Murad's question, if the meteorite can be dangerous when it falls because of radiation. So if you could just say a few words about it before we move on.
Sure. Okay, they are not dangerous because they are radioactive, but the radioactivity is very, very low. It's not, it's even less or the same level of a normal terrestrial rock. So it's not dangerous for our health. We always say to people, please do not touch the meteorite with your hands, but it is not because they are in principle dangerous, but it is because our hands, even if you wash your hands before touching the meteorite, you have not dirt, but the grease, no? The grease of your, and so you can contaminate the meteorite. So given that the meteorite was very recently fallen, it's very clean, let's say, we don't want to contaminate it. So what we ask is to record the position with the GPS in order to have the precise coordinates, to take some pictures, and then to recover the meteorite, the candidate meteorite, and to put it in a vase of glass vase, for example. Try to close it hermetically. The big problem is humidity, is water. Water is not a friend of meteorites because of iron, that oxidation of iron, rust. So this is, and then call us or somebody who can confirm that it is a meteorite or not. But they are not dangerous unless you are there when they fall. But
we are dangerous for them.
It's not very likely to happen.
Well, super. Thank you, Danielle. That was awesome presentation.